So we already went through this. My name is Xavier Avrillier. I'm a solutions architect at Giant Swarm. I focus on the on-prem and hybrid environments, and I've been doing this for a few years. My background was originally with VMware and virtualization in general. So I just wanted to preface this talk with a short statement about the fact that, well, cloud native days, but we are in the cloud native era, not the cloud era, just like 10, 15 years ago, where companies were moving VMs to the cloud and calling it today. It's not really like that. So now we can be cloud native on premise, on bare metal. It doesn't matter whether it's in the cloud or somewhere else. So you've all seen, I think, this diagram in some form or another. On the left-hand side, we have the virtualization stack, where we have a host OS, a hypervisor layer, and then we have our guest OS for each VM, and we have container engines, etc., for our Kubernetes nodes. Whereas on the right-hand side, we have what it would look like for hardware servers, so bare metal. So we get rid of that hypervisor and this kind of duplication of guest OSs for the VMs, and we go straight on the hardware. So we have only one host OS, and then we can share our container engines, our binaries, libraries, etc. That bare metal host was generated by DALI, by the way. I was pretty happy with it. So when does bare metal make sense? Of course, cloud and virtualization is much more flexible and easy to use. However, bare metal has some benefits. For instance, like I mentioned, we don't have this overhead of having a hypervisor and a bunch of guest OSs that will snatch some of the resources of our environments. The resource scheduling happens at the Kubernetes level. So I mentioned the CPU ready metric here. So instead of having, like in the virtualization stack, you have a bunch of virtual machines. So your hypervisor needs to schedule those virtual CPUs on the physical cores. If you over provision, then the virtual CPUs are going to wait for the physical cores because the hypervisor is doing that. So your guest OSs, your Kubernetes nodes, think they have a certain amount of CPU, but in fact, they are actually waiting underneath. So when you're working with Kubernetes level, we have visibility and all that stuff. Of course, we have direct access to the hardware. So like these days, GPUs for AI and all this stuff. And you probably won't have to pay 10 times the price to keep using VMware after Broadcom purchased the company. But, so anyway, so there are lots of benefits to bare metal, but there are also some cons to it. So hardware is slow. So, you can't really create physical servers like you create virtual machines. You have to order it from your vendor. You have to configure it, rack it, patch it, etc. So all that stuff takes time and adds overhead. It's not flexible. You have to manage firmwares, drivers, all these things. Hardware breaks. Whereas if your virtual machine is not going to break, if your host dies, then it's just going to restart somewhere else. And same in the cloud, like you don't have to worry about where your instance runs. So basically, hardware is just harder, and this is what we are here for today, and to try and address and see if we can make it a bit easier. But first, let's take a quick look at Kubernetes, because this is also what we're going to talk about. So what is a Kubernetes cluster? On the left-hand side, we have a control plane, and on the right-hand side, we have worker nodes. So the control plane is an odd number of Kubernetes nodes with a Kubernetes API, the core controllers, and a database to store all that stuff, which in most cases is etcd. And then we have the concept of node pools. So node pool is a bunch of Kubernetes nodes that have the same configuration. So if, for instance, if you have some nodes with GPUs assigned, some other nodes with specific networks, so we can define our areas in terms of machine pools, node pools, sorry. And creating Kubernetes clusters is not say crafty, but there's many ways to do it. And people have been using different ways to do it over the years. So there's the traditional Terraform with Ansible. There are products like K8s, KubeSpray, the vendor-specific solutions, and also Giant Swarm. We used to have our own operator since 2014, 2015 to manage Kubernetes clusters on infrastructure. But then a few years ago, Cluster API came along. And Cluster API is a great project originated from one of the special interest groups in the CNCF, in the Kubernetes. And this is an extract from the documentation. So Cluster API uses Kubernetes-style API and patterns to automate cluster lifecycle. So instead of running playbooks or going and create the resources yourself, you just create some resources in your Kubernetes cluster, and then some operator is going to do all that stuff for you, so you don't have to do it yourself. And if you want to have a look at one of my colleagues' talk that he did to a few conferences in Europe lately, this is how Giant Swarm migrated from our custom operator to Cluster API. We used to have our own in-house thing made, and we decided to transition to Cluster API for consistency's sake and community support and all these things. So this is a 10,000 foot view, let's say, 5,000, doesn't really matter, of how Cluster API works. So on the left-hand side, we have the concept of management cluster. So management cluster is just a regular Kubernetes cluster, except it's going to run our Cluster API controllers. So there are the core controllers, and then there are the infra provider controllers. So the infra could be AWS, Azure, pretty much wherever you want to deploy your Kubernetes clusters. So Cluster API is going to watch some custom resources, which are associated with the operator. And the infra controller is going to reconcile these things on the infrastructure. So the goal is from the management cluster to create workload clusters. Workload clusters are where our business logic and our apps are going to run. So instead of us or some playbook to connect to AWS and create the instances, the load balancers, etc., it's going to be our infra operator that will do this. So either you have someone that goes and create the custom resources, the CAPI resources in the management cluster, or you can have a GitOps framework, you have Flux, Argo CD, whatever, to run in your MC, grab that data from Git and apply it into the cluster. And in turn, the operators will reconcile all that stuff. And at the moment, we have 35 providers as of right now, June, and counting. There's more and more that are being added. So I expect in the next few months, years, there's going to be even more than that. So first of all, I'm going to look at how CAPI works, then we'll look at Metal3, and we'll see how these two things kind of tie with each other, with Cluster API and Metal3. So I took vSphere as an example because my background is as a VMware guy, and the vSphere provider is pretty simple, so it's a pretty good example for this case. So these are the 6 steps we're going to go through. Create the resources, and then we see how this stuff is being reconciled and how the cluster is provisioned. So the first one is we need to create some custom resources, like I mentioned. So the blue ones are the control plane stuff. So the kubeadm control plane resource will introduce all the specifics about our control plane. So what you want your API to look like, etcd, how many replicas you want, how you want to bootstrap your nodes, so files, users, scripts, all these things you can specify in that resource. And then we have an infra machine template. So in this case, it's called vSphere machine template, but could be OpenStack, AWS, Azure, anything that you want. And this will define what the VMs backing the Kubernetes nodes should look like. So, CPU, memory, basically the VMware specific stuff. In yellow, we have the worker nodes. So I mentioned node pools earlier. In this case, it is called machine deployment. So a machine deployment is going to define what the node pool should look like. How many replicas do you want? Like specific failure zones, etc. We had the bootstrap data, which is split. So in the kubeadm control plane, we had everything in one CR. Here we have the machine deployment and the kubeadm config templates, which will introduce all the bootstrap data and everything that we need to turn a machine into a Kubernetes node. And the same infra machine template for the VM. So we can have multiple machine deployments. So it is the same pattern as Kubernetes pods. So you have the deployment, the replica set, and the pod. Here we have the machine deployment, the machine set, and then the machines. So this is how we can handle upgrades and rolling nodes. And finally, we have cluster CRs, which include our service-side, spot-side API endpoints, the vSphere credentials, period domains, anything that is cluster related, basically. So at first, our controllers are going to pick up the CRs. Our CAPV controller, so CAPV stands for Cluster API Provider vSphere, is going to check our vSphere credentials. I pick vSphere because it's faster, like it's easier to explain. Like there's no, if we were using AWS, you would have to create a VPC, you would create the load balancer, all that stuff. In vSphere, it's much simpler since it's just a dumb load balance, dumb hypervisor, basically. Once the vSphere credentials are validated, we have a machine deployment and the kubeadm control plane with a number of replicas I mentioned. So according to those replicas, we are going to, the CAPI controller is going to create a number of machine CRs, which will define our Kubernetes nodes. For each machine, we will have vSphere machines and kubeadm config, which is generated by the Bootstrap controller. So the Bootstrap controller, in most cases, is going to be kubeadm. This is what most companies use. But there are other controllers like, Sidero, Talos, and yeah, there's a bunch of other providers that we can use as well. So this Bootstrap data is attached to the vSphere machine and stored in a secret. So we also call it user data, and that stuff is going to be used by Cloud Init or Ignition to initialize the machines into Kubernetes nodes. So once we have done that, the CAPV controller is going to pick up our vSphere machines and is going to use all these properties to clone a template into a VM. It's going to pass that user data as metadata to the VM. So it uses a specific field that can be used by the VMware tools inside the guest OS and by the logic embedded in Ignition for Flatcar, CoreOS, or Cloud Init. We are going to use a specific data source for VMware that will look inside the VMware tools guest properties, grab the data, and initialize the machine using that. So the first control plane is going to run kubeadm init, and the subsequent one are going to join the cluster. This is simplified quite a lot, but at this point we have a cluster basically, and we have a specific secret in the management cluster, which will contain our kubeconfig. So you just grab this kubeconfig, you dump it to file, you do your kubectl get kubeconfig this file, and you can list your nodes. And at this point, they are going to be not ready. So you need to install your CNI, your CPI, core DNS, pretty much everything that you need in any Kubernetes cluster. At this point, you're okay. You have a cluster. It's running. It's being tracked by the management cluster. And you can install like core DNS, CPIs, and stuff. You can install it with a feature called Cluster Resource Set, which is a feature of Cluster API. But there are all other things like Flux Helm releases that can do this. Depends on how your teams want to manage the lifecycle of your apps. And this is what it looks like pretty much. At the top, you have the machine CRs that define our cluster. So we see the 3 control plane at the top, and then our machine deployment with 5 workers. So this one, Grouse, is one of our management cluster that we use for end-to-end test. And you can see the status of each node, the version they are running, can get a whole bunch of other information. At the bottom, we have cluster.ctl, which is a cluster API CLI provided by the project, where you can see some specifics about your cluster API provision cluster. And if you want to know more about Cluster API, this one is a very good talk from a buddy of mine, Erkan Erol. He did it to KCD Turkey. So the talk itself is in Turkish, but these are just the slides, but they are great because they are quite self-explanatory. So I really recommend it. It's very, very helpful. So in CAPV, we have the vCenter API to talk to, but how does it work for bare metal? We don't have we don't have anything to talk to you like we would think. So what are we going to do? This is where Metal³ comes into consideration. So we're going to check it out and see how it differs from the other providers. Just going back to the same concept I just explained, in this case is AWS or CAPA, Cluster API Provider AWS. So you have your MC, Cluster API talks to AWS, and then AWS takes care of everything in the background. So we don't really need to worry about any of that. But in the case of bare metal, we need a few extra steps for it to work. So we're going to talk to the BMCs, Baseboard Management Controller. Also, you might know them as Dell iDRAC, HP ILOs, Fujitsu IRMCs, and all these out-of-band controller cards. And we have a software called Ironic, initiated by the OpenStack Foundation, that will talk to the BMCs. Ironic knows about all these vendor protocols and knows how to talk to these things in order to operate what we want to do based on other operators. So it can use Plexi, Redfish, IPMI as well. So it doesn't necessarily need to be iDRAC or ILO. On the Kubernetes side of things, we have Metal³ starts with the bare metal operator. So the bare metal operator is going to watch some custom resources we'll talk about in a bit, but bare metal operator is going to be the link between the hardware world or the outside of Cluster API world and our management cluster. And in between these two things, we have the CAPI provider. So I talked about CAPV, CAPA. This one is called CAP-M3, so Cluster API Provider Metal³. But yeah, bare metal operator is going to be the brain of the operations here. So let's take a look at what Metal³ contains and what it's made of. So at first, we have a few infra PCs that you would find on any normal network. So we need to have some IP addresses for our nodes to Plexi boot, for instance, if that's what we want to use. We need to have a web server to serve OS images. So if you're going to use Kappa, for instance, you don't need to worry about that because by default, you can use instance types. But here we have to take care of that ourselves. So we need to either build the images or take them from somewhere else, like Exoscale, for instance, serve them on the web server so that our stack can consume them. And of course, we need physical servers that are compatible with Metal³ with an out-of-band management card. So first of all, Ironic, like I mentioned, it is the backend of Metal³. It's kind of the unsung hero that we don't see behind the scenes. So if you want to thinking about vSphere to compare, it would be the actual host the service, creating the files, creating the VMs, like everything that we don't see when we create a virtual machine. Same thing in cloud providers, for instance. And this is an extract from the Ironic documentation. So API driven, API first. And it is kind of a gate into the hardware world without having to know Redfish and every single BMC protocol. So we just talk to Ironic, and then Ironic will take care of the rest. So we don't talk to Ironic directly as operators. This is done by a bare metal operator. But the Ironic is made of a few things. So we have the API, of course, that we talk to initiate all these things. We have the conductor, which will run the commands against the BMCs. We have the Ironic Python agent, IPA. So it is a small RAM disk that will run in RAM on the servers. And it will take care of some things for us, like cleaning the disks, writing OS images to disk, hardware inspections, all these things. So it's pretty much like our agents on the field doing some work for us. Then we have the inspector that will take care of grabbing whatever hardware and what capacities our servers have. And of course, we need a database to store all that stuff. Then we have BMO, bare metal operator. This guy runs in the MC, management cluster. It manages the lifecycle of our physical servers. So for each physical server, we'll need to create a bare metal host custom resource. Bare metal operator can be used independently. You don't have to use Cluster API, but the idea is to use it with Cluster API. Otherwise, it doesn't really make that much sense. So the one bare metal host for each physical server, and we'll see in a bit what these guys look like. So the bare metal host CR, by changing some of these fields, some of the specs, we can do a bunch of things like power off, like manage the power status. We can change firmwares, change settings, etc. So we can basically manage our physical servers by amending those CRs. So what happens when I create one of these? This is the minimum specs for a bare metal host. So we have the IP address, the protocol, secret with the credentials, whether we want it to be online or offline. So we have a few different things like that. There are many states that the bare metal host will go throughout its lifespan. I won't go through all of them, but we'll see a few states and what they mean. And this is how they relate to each other. So it looks a little bit like a madman's invention, but when you start getting into it and really looking at each states, it kind of start to make sense. So it's not as crazy as it looks. So we created our BMH for bare metal host server. It goes briefly into the creating states. Then the bare metal operator is going to validate the credentials of our iDRAC, for instance. Let's call it iDRAC, and change the states to registering. The bare metal host is going then to go to inspecting, because at this point, from a Kubernetes point of view, is just an IP address and a secret. So we need to know what this hardware can look like and can do. So we're going to inspect it. And the inspection phase is the interesting part, actually. So at first, the Ironic is going to order the BMC to mount this IPA RAM disk that I mentioned, which is exposed by Ironic itself on an HTTPD endpoint. Run it in RAM, starts on this RAM disk, and then it's going to look for the hardware by running a bunch of Linux commands. So it's going to check CPU, memory. We'll see in a bit what it looks like. But it's going to collect all the data for us and send it back to Ironic, which will expose it for bare metal operator to consume. So once it is grabbed by bare metal operator, it will be put into a hardware data custom resource, and that hardware data is also put in the status field of our bare metal host. So at this point now, we know what the server looks like. We are in available state, and available state will mean that we have this machine that can be consumed. So not like, it's pretty much like a pre-created virtual machine or AWS instance. Here we have this host that can be used to create a Kubernetes node. And yeah, this is what this hardware data look like. So there's quite a few fields. This is cropped, but there's stuff about the hardware, pretty much what you can find in your BMC UI, but crammed into like a CR in Kubernetes. So the interesting part is the storage devices in this case, I find at least, because you may have several disks and you want to know where you're going to install our OS. So now that it is available, it's ready to be provisioned. What we are going to do is change that bare metal host, give it an image to use. So by image, I mean the OS image that is stored on the web server. We give it some user data. So how to configure the OS, like I mentioned, the bootstrap data, this is what I meant. And which storage device to install it to. So we just changed these few fields. And then, so this is what the user data would look like in this case. I'm just setting a bunch of HTTP proxy variables, restart containerd, install my SSH key. This is kind of, simple basic stuff just to show what it looks like for CloudNative, for instance. And while in vSphere, we use the metadata field on the virtual machines, here we don't have this luxury. So Ironic is going to, like the RAM disk, is going to create a tiny partition on disk called the config drive, put the bootstrap data into this partition, and then when we restart the machine, the OS, CloudInit or Ignition, is going to pick up data from that partition and then initialize the server and turn it into a Kubernetes node. So this is kind of what the workflow looks like. So the IPA RAM disk is going to grab the OS image from the web server, write it to disk. So it's not booting on the OS image. It's the IP around disk that grabs it, HTTP, and then writes it to disk. And when it restarts, it will pick up the data from this tiny partition that I mentioned, the config drive, and initialize the disk. Once it's done, we switch to provision state, meaning our bare metal host is provisioned and running the OS image that the whole purpose of its life was. So where does Cluster API fit in here? So I already showed this diagram here. It fits right there between bare metal operator and Cluster API. So it has the easy job, basically. All it needs to do is what we just did manually ourselves. So it's going to change the image, like certain image, OS image, and the user data to configure the OS. The extra step is that it's going to pick up one of the bare metal hosts to provision the machine. So you can specify, you can have labels and stuff to pick whichever bare metal host you want to use, because they may be in different racks, different buildings, they might have different hardware configurations. So you need to be able to pick specific hardware to provision your node pools. And instead of writing the user data ourselves like I did with the HTTP proxy variables, this will be created by the Bootstrap controller automatically. So I mentioned kubeadm config templates, kubeadm control plane. This will come from there. So the Bootstrap data will be much longer and will be much more complete. So we can have like a full-featured Kubernetes node. And yeah, like visually, that's what it looks like. Sorry. So instead of creating vSphere machine templates, we're going to create Metal³ machine templates. So we have a bunch more custom resources for Metal³. But essentially, this is what it looks like. So when we create a cluster, we'll have Metal³ machines. CapM3 is going to see those Metal³ machines, grab a bare metal host, give it to that Metal³ machine with an owner ref. And once it changes the OS image and user data, the bare metal operator will pick up the change, and we go back to what we just saw earlier with ironic, etc. And the rest is pretty much like any other cluster API provider. So when we bootstrap the cluster, we're supposed to have a bunch of bare metal hosts available for consumption. So Metal³ picks them up, then bootstrap the first control plane node, then it scales the control plane to how many replicas that you want, and then the machine pools are provisioned. You still need to install CodeDNS, CNI, etc. So pretty much the same. Once you've passed this Metal³ part, it is just business as usual in a way. A couple interesting things about Metal³. There's a lot more, but I don't really have time to go into much detail. But first one, it is kind of slow. So especially if you take the inspection phase into consideration. So starting a VM is pretty fast. Here you have to go through checking the RAM, all the hardware inspection stuff. So it can take like maybe 10, 20, 30 minutes if your hardware is slow. But once the inspection phase is done and you have your bare metal host in available state, it's fairly fast, especially if they're already powered on. But yeah, it will be much slower than any other cluster API provider for sure. An interesting one is upgrading clusters. Because we can't just pop physical servers out of nowhere like we can with virtual machines, we might want to reuse physical servers so we don't need to have hot spares and have hardware capacity lying around doing nothing. So we can have a scaling. So instead of provisioning new servers and then deleting old ones one by one, we're going to do the opposite. We're going to deprovision old servers and then create new ones so we can get that bare metal host CR to go back to available states and then consume it with our upgraded nodes. And then we can do a few different things with annotations on the bare metal host. So we can inspect the hardware. So if you're going to add memory, change something, you can trigger an inspection. And from there, you will update all your CRs and your hardware data. You can manage maintenance mode. So if you want to keep a server down, you can use one of these reboots annotations. And you can have several people have an annotation with different values. So when all the annotations are gone, then your server is back into the game and can restart. But there are a lot more than that. We don't really have time, so I would like to thank you for your attention, and hope you have a great conference. Thank you.